you should start to memorize. All right, I wanted to also take some time. I have found some people found it's helpful if I go through Dr. Basu's equations with you. Remember, an IV bolus is a really straightforward proposition. You're giving a dose and you're giving it boom that fast. You're giving your dose at right away. It's all going in. You don't have to worry about any drug going out because it's instantaneous. So you automatically have your Cmax here, or your C0, whatever you want to call it, occurs right there. And that concentration is equal to dose over volume, isn't it? That concentration is dose over volume. So you start and stop giving the drug in an instant, so that the concentration shoots up and then it immediately starts to fall, doesn't it? That falling phase happens at a rate of K, right? You can determine K by comparing two different concentrations on that same line, and it's just rise over run. So rise, change in concentration, you have to consider this as a log concentration if it's a straight line over the change in time. And if we actually rearrange this equation, we get the equation that we use all the time, which is basically a one compartment falling phase equation that compares two concentrations. This one happens first, so you can call this one C1 and this one C2, or this one C0 and this one at time whatever t. But in any case, their relationship is described by this line, this equation, with E raised to the negative K, again, which is the slope of this line, times T, which is basically the difference in time, the same thing. This is just a rearrangement of this equation. So this T will always represent the difference between the time difference between these two concentrations, won't it? And that's what this equation is. Cp is equal to C0 e to the negative KT. There's our one compartment falling phase. As long as you're not giving drug, this always describes those concentrations. So you can't be giving an infusion. You can't be giving an oral drug because you could still be absorbing drug, right? Then we also know that this C0 is the same thing as dose over volume. So this is just this same equation, only saying dose over volume times e to the negative KT. As we've discussed before, area of the curve is equal to either bioavailable dose, you could put a salt form on here too, over clearance. If it's an IV, remember, if it's given IV, the F is always 1, right? Because what's the definition of bioavailability? Bioavailability is the fraction of drug that we give that actually makes it to the systemic circulation. And if we're giving a drug into the veins, right into this, we're giving it right into the systemic circulation. So all of it makes it no matter what. Now that same drug may have an F of 0.2 when given orally, right? So the F depends on if every drug's F is going to be 1 if given IV. So if it's given IV, you don't have to worry about the F. You'd still have to worry about the salt form if it was given as a salt form. But remember, clearance is really what's happening here, right? It's really dose over clearance. However, if we want to figure out the clearance, we can do that by using the volume in K, can't we? Because we know that K is equal to clearance over volume, which means mathematically clearance can be determined by V times K. But it's really important to understand that volume does not determine clearance and K does not determine clearance. K is determined by clearance and volume, but you can use it mathematically here, can't you? So this is stuff you should really should be fairly straightforward for you. We know total body clearance is the addition of all of the different organ clearances. There are some exceptions to that, but that's a basic rule. Same thing with your elimination rate constants. I don't think you discussed this too much, but your renal clearance can be calculated if you look at the dose over area of the curve Well, we'll get it. Don't worry about this. I don't think he went over it. Now, what you need to realize is be able to actually interpret what this is. What is this right here? Well, it's dose over volume. If you're giving it as an IV push or IV bolus, this is C0, isn't it? And then what's this? This is the same thing. So these two things together is the same thing as this equation. So this is C0. This takes you to any concentration time T after that C0. And then what is this? That's a multiple dosing function. So the multiple dosing function, remember, is your magic carpet ride that'll take you to the nth dose. So this is going to take you to whatever concentration at time T on the nth dose, right? So so if you put all the pieces together, you can figure out what this is. So this is C0. This takes you to time T after that, somewhere here. And then this is your multiple dosing function. Okay. This is your renal function. I don't think you need to worry about that. Now, you also, what if you wanted to take, what if you wanted to figure out some concentration at time T after the initial dosing function at steady state? Well, you would just take your multiple dosing function. Your multiple dosing function is 1 minus e to the negative nk tau all over 1 minus e to the negative k tau. At steady state, this n is going up, right? So as this number goes up, this whole thing becomes 0. And we end up having 1 over 1 minus e to the negative k tau. So this is your accumulation factor, or your steady state factor. So this takes you on a magic carpet ride to steady state, doesn't it? So you could just replace this with your steady state function to take you to steady state, can't you? If you know your Cmax at steady state, you can get to Cmin by just using your falling function to go from your Cmax to your Cmin. And remember, if you're giving it as an IV bolus, here's your Cmax. And if you're going to give this here at tau, here's your Cmin, right? And if we're at steady state here, we can figure out our min pretty easily. We just need to know the difference here, which is tau. So e to the negative k tau. Okay? It's not, hopefully that helps. This is not anything magical. Now, what if you're giving an infusion? All right, so if you're giving an infusion, we're not having our dose go in and having us go up to a Cmax here right away. We are starting an infusion where we're starting from 0 and we're giving this at a certain dose rate, or if you want to call it an infusion rate, whatever you want to call it, this concentration is going to start to increase based upon the dose rate in and the dose rate and the clearance, right? So we know that, that CSS average is equal to bioavailable dose rate over clearance. Do we have to worry about bioavailability here? No, because we're giving it IV. So it's just dose rate over clearance. You already know this piece, don't you? That CSS is dose rate drug in over drug out. So we know that that's the relationship. So that's what this equation is here, right? This is CSS is equal to dose rate, KO, or dose rate, drug in over drug out. This is just clearance, isn't it? K times VD is clearance. So if you think of, you don't have to know anything new. This is dose rate over clearance, which you already knew would equal your CSS. Now, this is CSS too, right? Dose rate over clearance. What's this? Well, this is the fraction of steady state that you've achieved at time T. So if you're giving your infusion, and let's say you stop it right here, you're not at steady state yet, or maybe you are, but let's say you're not at steady state. So this is 1 hour into the infusion and we stop the infusion. So we don't go on to steady state, right? So we stop the infusion. So wouldn't we want to know what fraction of steady state are we at here? Because we could just say our dose rate over clearance and multiply it times 1 minus e to the negative k, in this case, 1 hour, or really it's your time of infusion. And that will give you your concentration at this time, which is usually C max if you're giving a short infusion, isn't it? So this equation gives you C max or anytime CP along this line here, right? But usually if we're giving a short infusion, this is C max. And then how would we get a C max at steady state? Well, we would multiply this times 1 over 1 minus e to the negative k tau, because that's going to take us on a magic carpet ride to steady state. So that becomes max at steady state, dose rate over clearance times 1 minus e to the negative k, time of infusion over 1 minus e to the negative k tau. And once you have your max at steady state, you can figure out your min by just using your falling function, right? So let's say this is your C max at steady state. And this is your C min. We can't just use tau here, right? Because we had some time of infusion. So the difference in time between these 2 points is tau minus time of infusion, isn't it? So that's what this is. To take you from your C max to your C min, it's just tau minus the time of infusion. Don't make this more complicated than it is. I often draw pictures so that I understand what the difference in time is, and maybe that will help you as well. Loading dose KO over K, I've never used that, but I guess you can use that equation. Let's look at this. So here we have a concentration at the nth dose. So we're going to use the multiple dosing, or the multiple dosing function, which is right here at the nth dose. And if we want it to be, we can figure our max. If we know the max on the first dose, we can just fast forward to whatever nth dose after that, right? And then of course this is, let's just use our detective. This is our CSS. This takes us to C max, doesn't it? Not our our CSS. This takes us to our C max once we add this in, and then this takes us to any time t after the end of infusion. If we wanted to take this to steady state, we would add on let me erase some of this stuff. We would add on our steady state function, or our accumulation factor that would take you to steady state. Or we could take you to the nth dose, right? Whatever you want to do. You just have to know what all these pieces parts are and just build your equation however you need it to solve the problem. Now here's for oral absorption. Notice here that we still have a function of dose over clearance, right? And then you have to consider bioavailability. I usually kind of think of it as F dose over volume times this interaction between the rate of absorption and the rate of elimination, right? So as you're absorbing drug, but you're also eliminating it this whole time, right? And then when you get to your T max, Ka is equal to K, so they're both equally important. And then the K of elimination starts to win and the drug starts to decline. Now, could it still be being absorbed here? Yes. So you can't really use just Ke in this case. This isn't necessarily Ke because it's still got some Ka in there, doesn't it? So you can figure out your concentration at any time t here, but you have to consider both the Ka and the K here. And this is your same falling function, but this is the drug actually being absorbed, and you have to subtract that. So you have to think about both absorption and elimination, and this relationship figures that out. So at any time t, when you put, let's say you want to know what it is at 6 hours. So you put 6 in here for your t's, and then just plug and chug for your concentration at 6 hours in. Your peak time or your Cmax, it can be calculated, your Tmax, by the relationship between these Ks. Just plug and chug. You already know that your bioavailability can be calculated by comparing your area under the curve over dose IV. Put that in the denominator because that's the standard, right? Because that's got a bioavailability of 1. And then this is by giving it by any other root, right? This is actually a trapezoidal rule, right? So these are all the different trapezoids. And then this is just your last point divided by K, which we've already discussed. You already know the multiple dosing function. You know the accumulation factor. Takes you to steady state, takes you to dose N. Area under the curve. Area under the curve, that's given to you a couple of times there, right? Drug in over drug out, bioavailable dose rate over clearance. This is dose rate, dose divided by tau. I just like to think of it as dose rate. I think it's easier. Multiple dosing, so at any concentration N here. He's repeated this many times. He's very nice in giving you all these equations. Cmin at steady state is going to be your first Cmin times your accumulation factor, right? This is your ride to steady state. Same thing here. All right. This also may help you with your reabsorption. This is just the Henderson-Hasselbalch, isn't it? All right. Well, I hope that helps. All right. Thanks. Bye.